Welcome everyone to our Spectrum X Radio Shop chat on RadioHound. My name is Nick Lanneman and I'm the Spectrum X lead and I'm co-director of the Notre Dame Wireless Institute. Before I hand things over to Bert Hochwald, my colleague, I want to just give you a little bit of a backdrop on this session and the team that's organizing it. So Spectrum X is the merger of 4 planning grant teams that are pursuing the NSF's Spectrum Innovation Initiative Center. We've put together a team of 27 universities, which includes 15 minority-serving institutions that we're really excited about, the National Radio Astronomy Observatory, Virginia Diodes, and a number of collaborators. Now, our full proposal is being reviewed by NSF, and we continue to interact as a center as part of our planning process. And these radio shop chats, like this one, are an example of that. So just to set the context for this presentation, these radio shop chats are informal presentations and in some cases panel discussions involving leading experts in spectrum-related technologies, economics, and policy. The purpose of these chats is to educate, debate, and build community. We're really excited. We've already got 49 participants on this call. That might be one of our that might be our record, so we're excited about that. Thank you all for joining us. The audience includes university students, both graduate and undergraduate students, faculty, staff, as well as many industry and government employees. We are recording the session so that we can review it internally and share it with members of the team that can't participate. We only do so with permission. And we also operate under the Chatham House rule, which means that you're free to use the information you obtain here from today's discussion, but you're not allowed to reveal the source of that information without their permission. So if there aren't any questions about our format, once again, welcome. Thank you for joining. Let me introduce the topic and our speaker. So the topic will be the RadioHound Spectrum Sensing Platform, and it will be presented by my colleague, Bert Hochwald. Just for context, RadioHound is a project that we started here at Notre Dame about summer of 2015, so we're about 6 years into the project. It started under our NSF IUCRC program. It was led by Bert, and he pulled a number of faculty, myself included, students and staff along with him. The project has benefited from a fairly sizable amount of additional funding from several industry partners and government agencies, and a significant amount of co-development with the Army Research Lab, which we should acknowledge. In recent years, our team has conducted field tests with ARL, as well as a feasibility study recently with the FCC and the Postal Service, and we've been exploring deployments of RadioHound within the NSF's power testbeds. So I'll let Bert take it from there when he gets into the details of the project. Let me just go ahead and introduce Bert and provide some highlights about his illustrious career before he takes over. So very fortunately for our team here at Notre Dame, Bert joined us in 2011 after a very successful career in industry. He spent 9 years at Bell Labs and 5 years as chief scientist and vice president of engineering at a company called Basim that was later acquired by Broadcom. There are many accolades in Bert's resume. The couple that I'll highlight is he's an IEEE fellow. He's won a number of IEEE paper awards and been recognized as a Thomson Reuters ISI highly cited researcher. And most recently, he was elected to the National Academy of Inventors for his 47 US patents. Bert's taken a leadership role in a number of projects, including the RadioHound project, and he's helped our institute really mature in the sense of building our own hardware and even software-defined radios instead of using COTS equipment, which is often more expensive and harder to debug. It's been a real pleasure working with him, and I'm really grateful that he agreed to give an update on our RadioHound platform today. Take it away, Bert.
Yeah, thanks a lot, Nick. Let me share my screen here. I think this is working out. Right. So, yeah, as Nick said, this has had a bit of a number of years of development behind it at this point, beginning with the IUCRC, this NSF program, Industry University Cooperative Agreement. Most recently, we've received some funding from the NSF through this ML Wins program. So we have Intel also to thank on at least part of what you're seeing today. The whole idea behind the project is the thought that spectrum sensing in one form or another is an important thing to do. And most importantly, in order for this to be successful, we'd want it to be cheap and ubiquitous, meaning if we carried sensors around on our phones, for example, and it didn't consume a lot more power than our current phones do, and didn't make our phones any more expensive or only a little bit more expensive, then it might be feasible. And so part of the project is to explore the boundaries on just how what we can get away with in terms of what would still be a useful sensor that could be low power, cheap enough, and low cost enough, and so that we could really deploy them in large quantities, say, hundreds of thousands, millions, or even more. And so we'd really get sensing everywhere all the time and really be able to get a good picture of what's going on over a variety of frequency bands of interest. And I'll have a little more to say about that. So there are a lot of people to thank, and I'm not going to try to thank all of them. There's a whole variety of students that have been involved in this, some of whom are graduated and not on this call anyway. But a lot of the work you're seeing is in fact done by graduate students. We have also on the call today, Randy, who'll come in later and help to run a demo. And of course, like with any live demo, we're going to see how well that really works. But Randy Urban is our software technician who / engineer who helps to glue everything together and keep things alive. And when ever grad students get involved, especially on things like software, it can be a hodgepodge of things and hard to manage. And so Randy's been invaluable at keeping the graduate students honest, and also in developing a lot of the back end aspects of the whole project. So let me get into it, because pretty soon we'll be out of time if I do all the acknowledgments. So the motivation behind everything is large scale spectrum sensing. You have a pictorial. Everyone's seen the spectrum analyzer on the left, which is on the order of tens of thousands, if not $100,000. If you want a reasonable frequency range and you want a reasonable sensitivity, there's handheld units that drop down into maybe $10,000 range or a little more. There's SDRs which can run in the hundreds, can often somehow magically make it into the thousands anyway when you add in all the options that you want. Then there's these smaller various project type RTL SDRs and whatnot that are one-off sorts of things where you have some semi-custom type of software-defined radio, which does some of the things that you may want, and maybe has a frequency range of interest to some degree, but doesn't quite hit the power or the sensitivity numbers you want. And so on the far right, we're targeting where we want to be, which is sensors that cost maybe, at least on the discrete part list, cost just dollars and in bill of materials, and so can be thought of as, if we were able to integrate this thing into a unit, we might actually get it down into the pennies. We're still a ways from that, but it's nice to at least think about it that way. Now, the idea is, of course, that if you really could get a sensor on every phone, like I was saying at the introduction, that perhaps we can get away with a sensor that really doesn't have all of the quality metrics that you normally associate with radios. You want extreme sensitivity. We want very high dynamic range. You want large tuning range and large instantaneous bandwidths. All these things that all the radios that you ever buy, have lay claim to, but perhaps you don't need any of these things, or maybe only a small subset of these things, if you're going to have everybody doing them, and therefore maybe we can get away with something a lot easier. So our vision is a bit of a real-time traffic, if you will, except on the radio spectrum. And so if everyone's carrying one around, perhaps you can aggregate all this data into a meaningful, say, spectrum map that you, much in the same way as when people report their traffic data as driving around on various roadways, report their speed information, and tell you which roads are worth traveling on and which ones are all congested. By the way, if there are questions, I will make sure that we move along at a fast enough clip that we can address questions as they come up, or we can wait at the end. Either way, I don't know, Tiffany, if you have a preference on that.
It doesn't matter to me. It's your call.
Okay, so if something pops into your head, feel free to ask it. I probably will skip this. I've been motivating the idea that if you try to get high quality spectrum sensors, you know, the curve on the in the quality versus cost per sensor. Hold on, let me get let's make sure I can draw on the screen here. So I'm looking at this right here at the moment. Everybody knows that there's sort of a sweet spot in terms of trying to get cost low when you're talking about sensors and radios. If you want an extra bit of resolution, everyone knows another bit of resolution is going to cost you dramatically twice as much as a system with 9 bits is often twice as expensive as a system with 8 because of all the overhead associated with getting higher resolutions. Also, when you want to create a system where you know that you need a lot of sensors, because it doesn't really pay to have a single sensor of extremely high quality that cannot compensate for having several sensors of lower quality distributed around an area if you want an accurate spectrum map. Of course, a single high quality sensor will tell you very accurately what's happening then and there at that particular spot. But if you move your antenna even a little bit, or if you watch as time evolves and the environment changes, that reading, even at that very high quality sensor, is going to bounce around all over the place. So you really need lots of sensors, and you can't have extremely large number of these very high quality sensors without it quickly getting cost prohibitive. So here I've attempted to just qualitatively draw that there's sort of a sweet spot. If you have a particular system performance that you're targeting here, then if you really want to minimize your total cost, you really want to be on the low quality side and compensate for that low quality with having more quantity. So first thing we did, let me clear this, is to work on developing the sensor. And I won't go through the whole history of it. Just needless to say, our first one in the upper left is pretty crude and involved lots of design boards and evaluation boards from various companies before we started to integrate things. Version 1 actually used an RTL SDR. So I'm looking at this one here. The RTL SDR is not shown. It's plugged into the USB port. So we had an external digitizer on version 1, and in fact also on version 2. It's only when we got more recently to version 3 that we incorporated a digitizer on board and got our bandwidth up to 20 megahertz instead of the 2 megahertz that we started off with. Now, in the end, if you compare these specifications, the tuning range, the bandwidths, the power numbers, not any of it is super cutting edge on any of these. You could probably say I have a sensor like that somewhere buried in a drawer somewhere. But the whole idea behind this is not just the sensor itself, but it's part as an overall system. A little more on the specifications here. The picture here now is of the version 3.1. We have a version 3.2 in the works right now. You're seeing sort of a picture of some of the things that we have on the sensor. We have an onboard processor, an MSP processor that helps to control our scanning, sensing, bandwidths, and control of the various other components, turning things on and off to save power and whatnot. We have a high band. It goes from 1 to 6 gigahertz, and a low band of 100 megahertz to 1 gigahertz. We need to separate that out because of the relatively large tuning range and the likelihood that we'll be using separate antennas for each anyway. Some tables here indicate some of the numbers in terms of the sensitivity, compression, amount of gain, and various noise figures. It's kind of a high noise figure of 20 dB on, but this is at right up near 6 gigahertz. We haven't quite optimized our performance way up at those higher frequencies. Okay, the idea is that we have a sensor now. It's working. We can use it to measure I and Q samples of tuning in some frequencies and over 20 megahertz bandwidth. Question is how to incorporate this into a overall system and get something useful out of it. Just to emphasize that it is a real thing, just throwing some of the schematic. One thing I didn't point out here actually is that there's even on this sensor here, there's a GPS module. So as much as we think we know what people would like out of a spectrum sensor, we're always surprised when we hear what people say, oh, we wish it had this, we wish it had that, we should have beamforming, we should have all these things. But the GPS module seems to be of universal use in the sense of knowing where it is and what time it is at any given point. So our schematic here represents about 5 years of evolution with various students. And actually this version 3.1 has been largely designed by graduate students, not just electrical engineering. There was some computer science thrown in there too. There's a processor over in the corner here, the microcontroller down here, where this needs to be programmed separately. It's on the board, and so you need to worry about how you get software on and off the RadioHound board. The RadioHound board sits on top of a beagle bone. I'm not sure if I have a separate picture of the beagle bone, but the idea is that, and you can sort of see it in this picture here. The RadioHound board is on top here, but it's sitting connected to a computer, in this case, a beagle bone below through these headers here. And the idea here is that the beagle bone acts as a proxy for what a phone might be in terms of capturing data. In other words, the RadioHound does all the tuning and digitizing, and then it feeds the data to a host. And the beagle bone is acting as our host here. And it's not meant to be, the system is not meant to work in a proprietary way with the beagle bone. But in this case, the beagle bone, which is a Raspberry Pi, a brother kind of to the Raspberry Pi, some equivalent type of system, ended up being a convenient choice of being able to capture the discrete digitized samples from our RadioHound board. And so I've left that out of most of our discussion here. Again, back to the schematic layout, just as a way of picture here. Here's our GPS module. I don't know how easy it is to see those lines. Here's our MSP. This is our A to D converter. Some of this is on the front of the board, some of it's on the back. And of course, as with many of these types of pictures, it's very hard to get a nice three-dimensional view of things. PLL here, some various stages of amplifiers, VGAs and such, and here are our connectors. Just show you it's for real. So now that I've sort of semi-convinced you that there is a real sensor at play, the question is, how many of them will we need to infer occupancy? So this is kind of a part of what we're doing with Intel at this point, to say, okay, you have these sensors. We want to create a map of some area, which we call occupancy map. And we want to throw some sensors down. We clearly don't want to throw sensor down every place that we want to infer occupancy. We'd like to throw sensors down in either selective places or random places, and as few as possible, so that whatever measurements they make, we can infer occupancy over a very large area. And to that end, we looked at various models for how to connect what sensors measure to infer occupancy, and we settled on a neural network model that can be trained to take sensor measurements and infer occupancy from that. So the idea here is we throw sensors down, perhaps at randomly, and these are indicated by this kind of a, I don't know, measly looking diagram here, which has a bunch of dots on it. The dots here are intended to represent sensor locations over some geographic area. I think there's 100 in this particular picture. These sensor values are fed to a neural net through this aggregation step here. And at the lower right here is what we really want, which is an indicator of which areas have energy and which areas don't. And occupancy is defined as the energy exceeding some threshold in some frequency band. So there's a lot of dimensions to this problem. There's the frequency band, there's the power levels, there's the bandwidths. And necessarily I had to, in the interest of time, I have to keep the discussion kind of abridged in terms of all the specifications on that. But needless to say, when you do a real experiment, you have to deal with all that, and you can't just let it slide under the rug. But the idea here is that we want to create a spectrum map over a large area from a relatively sparse set of measurements here made by, if not the RadioHound sensors, some other kind of sensors. So I'll discuss that aspect of it just a little. Let me pause for a second and see if there are any questions.
There is one in the chat. Do you have a chat window up?
I can. Let's see.
Yeah, so the question about the GPS sensors or GPS location on each node, yeah, since they have a GPS chip on it, and assuming it has a lock, the node has that data that it reports back to the server with every scan that it sends back. So we bring that GPS data back to the server side, and then we can process it and locate it and know where it is geographically as well as time-based.
Great, thanks.
So how do we determine occupancy? Well, one student here in particular, Abbas, who's sitting just to my left, he has been working hard on this aspect of using the machine learning to infer occupancy from a very limited set of measurements. In this case, there's a picture drawn of a region in downtown Chicago where he threw some emitters down. These are these yellow dots that we see down here. And the power measurements there are, yellow means high power and blue, darker blue means lower power. You're seeing a relatively complicated looking map that's lit up by these emitters. And the whole goal of an occupancy type of system is, without knowledge of where these emitters are, without knowledge of how many emitters there are, without knowledge of what their power levels are, can you create a map like this one here from this set of sensor measurements here? Seems like a kind of a hard or impossible task because there's really only a very limited number of measurements. You do see yellow here indicates that that sensor happens to be measuring a high power. Well, it happens to be close to an emitter. Here's a sensor that's reading relatively low power. It seems to be along a little bit of a valley there. Clearly, for anything like this to work, it needs to be trained. And so you need to convert the sensor measurements into an occupancy map by a set of training vectors and the usual sorts of things that you do with machine learning. And that's what Abbas has been focusing on specifically with our sensors. Now, I forget the exact dimensions of this particular map. And when we go to a demo later, we're not going to be doing anything over any large area. We're going to be doing stuff over a relatively small area. But this experiment here is run over something on the order of 20 by 20 kilometer type of region, where we were able to get lots of very fine-grained data topography about the region so that we can create an actual accurate model. If we throw an emitter down, what will the power measurement be at any given location? There's a software package called ATOL, which is used a lot by network service providers like AT&T and Verizon and Sprint and T-Mobile and such, that they know where to place their base stations, at least to first order, to try to get good coverage over a given region. And they use pretty highly accurate topography and building information to figure that all out. It'd be onerous to try to do that extensively only through a measurement campaign. We use that same software. We can throw emitters down and figure out what the forward model is. So part of the step of this, and I'll just skim over this because the time is pretty limited. Like with any neural network system, we have a number of sensors that we have placed in an area. They move around. They're not under our control. We do know where they are because we have their GPS coordinates. We do know how many there are. We can tune them. We can control them. We can look at a specific frequency. We can choose whatever bandwidths we want. But in order to feed a neural network or a measurement system, they don't like variable inputs very much. Everything has to be given in relatively fixed sizes, if I'm not mistaken, especially if you're using image processing types of systems, which we do. They like fixed input, fixed output sorts of processing things, equivalent to, say, the resolution of a photograph. So you have to take this variable input, which is a variable number of sensors, you project it onto a grid, which is what we do called snapping the sensors or aggregating the sensors to an input grid. And so we just count up the number of sensors in a given grid location, aggregate their measurements together, and feed that to our neural net. And you're seeing the process of that in this particular drawing here. And we're comparing everything to a threshold. This result of this aggregation, which is given as this input over that grid, is fed into an encoder-decoder network. And not being an expert myself on the neural network side of things, I couldn't tell you exactly why we chose an encoder-decoder, other than we know that it works well on this sort of image processing. So you're seeing a relatively really sparse input here being asked to generate a relatively complex looking occupancy on the right. And these encoder-decoder structures are quite good at it. Wherever there's a sensor, we feed in the value of the sensor. Wherever there's no sensor, we feed in a 0 to indicate that we don't know what's there. And so this structure is very amenable to that. And on the right, you're seeing our estimate. Our T hat is our estimate of occupancy. T is our actual occupancy, and T hat is our estimate of it. And again, I'm not going to go into the structure of this network here. But just to give you some numbers on how this works, we fixed the number of sensors at about 100 in this particular thing, which ends up being about a 0.6 subsampling of an area, 0.6%, sorry, subsampling of an area. We vary the number of emitters from 1 to 40. We never tell the neural net how many emitters there are, where they are, what their powers are. And we create a spectrum occupancy map from that. And in this case, the emitters are assumed to be, the sensors are assumed to be our RadioHound sensors, which have a relatively good resolution. In our case, it's 8 bits of resolution. So the digitizing has 256 levels. And has a gain control and has all the things that you'd expect from a traditional radio. And as you can see here, depending on which topography you're in, the types of occupancy maps that you would create as a result of the topography is pretty dramatically different. Denver, where actually we'll have some more to say about Colorado a little later, obviously has mountainous areas in it. San Jose has some mountainous areas, but has a valley in the middle, and that big blue area is the valley. And depending on where the emitters are, you're seeing the occupancies vary accordingly. And in the case of, of course, the more wide open the space, the more contiguous the occupancies tend to be. And the more fragmented or the topography is, the more fragmented the occupancies, more fractal-like that they look. So things that have to work over a variety of different environments and circumstances. But extremely high accuracy is possible nevertheless. We get on the orders of 90% accuracy in predicting occupancy, which is a little bit startling if you have 100 sensors and you're trying to create a map that sophisticated looking. How can you get that kind of accuracy? Again, the details of that, we can do things like that, talk offline for people who are interested in more details on those aspects of it. I'm going to focus a little more on the RadioHound, the sensor itself here, but the purpose of this part of the discussion is to try to just motivate the path that we're on, and I'll say a little more about that now. Whoa, look at this, 1-bit sensors are okay. We suddenly switched, did a little bit of a bait and switch here. We took the 8-bit sensors that we had as modeled as our RadioHound sensors and said, let's pretend that we replaced the 8-bit digitizer with a 1-bit digitizer. What does a 1-bit digitizer do? It can only tell you if the power level is above or below some threshold, and that's all it reports. So on the left here, and this, lost my pen here. Great Apple stuff here. All right, so this is the ground truth of a particular region in Denver. The red dots indicate where the sensors are. The middle picture here tells you, based on those 100 sensor measurements, what is the reproduced or my estimated occupancy map. And visually, you can see, you can compare these two, the ground truth versus the estimated. And at least visually, it looks rather pleasing. It looks like most of the aspects of the occupancy have been accurately reproduced. This is with the full resolution sensors. But perhaps a little surprisingly, if we convert them all to 1-bit sensors and don't increase their number, just stay with 100 of them, we don't do that much worse, at least as far as pictures are concerned, which this goes along the thesis that it's better to have more sensors distributed around than to have high quality ones that are fewer. Now you could ask, where's the science and all behind this? And it is indeed not, fully developed yet, but we can say with some degree of certainty that with scaling up the number of sensors by a factor of 3 or so, we can recover everything the full resolution sensors could have done. So in other words, instead of having 100 sensors, maybe we should have had 300 1-bit sensors, and we'd get as much accuracy as the 100 full resolution sensors would be. And you say, okay, well, let's see, we went from 8-bit down to 1-bit, so we went from 256 levels down to 2. Then we increased the number of sensors by a factor of 3. So it's not, it's fairly clear that it's a winner there, but what actually is more important is that as we, like I said before, as we decrease the resolution of our sensors, the cost and power and things tend to fall exponentially with those number of bits. So having fewer sensors, having lower resolution sensors way over, it has huge benefits that extend well beyond increasing by just a factor of 2 or 3. I don't know if I explained that totally clearly. Okay.
We have a couple of questions.
Yeah, I could pause. I can't see them on this particular screen.
Okay. What frequency are these occupancy maps targeting?
These here are at 1900 megahertz, 2100 megahertz.
Okay.
But not we're not necessarily 2100 megahertz was taken as an example, not to be definitive in any way.
Okay, another one is there a trade-off between bit resolution and measurement coherence times?
Yeah, that's a good question. We do not yet have a good model for how time evolves. Right now, our measurements are being thought of as instantaneous. Of course, they're not, but the sensors report timestamps and location stamps with every measurement. So we can aggregate their measurements more or less simultaneously in time. And so we have not yet concerned ourselves with what happens as time evolves. I don't know if that answers that question.
The emitters are assumed to be continuously transmitting, though?
Yes.
Yeah. Okay.
The last question is, are emitters assumed to be omnidirectional?
In this example, I think, are they in this example? Yes, in this example they are. But again, our sensitivity to the behavior of the emitters is very low. We don't really have any model for the emitters. It was simple to make them omnidirectional, but if they had either an antenna pattern or some other aspects or tilt to them, or they were mobiles that are buried in somebody's pocket, I don't think that would have a strong effect on our outcome, because as far as we can see, we're not sensitive at all to either the number of emitters, their placement, their power, or any other aspect of them.
Okay, next question is, do you incorporate a frequency reference as well?
Well, we have a clock, which I didn't specify. There is a local oscillator on our boards. We do not yet correct that with GPS. That's one of the things that, depending on how accurate we really need to be, we have that on our list of things to do. But we have our own internal frequency reference that's accurate to 10 or 20 parts per million, or whatever the standard is for a lot of these crystals.
Okay, last one. Is the same 1-bit detector used across the whole spectrum?
Yes. All right. So I'm going to talk a little bit about the server architecture, and this place is where Randy can start to chime in, and I'll say a little, because there are words on here that I'm not sure I know exactly how to pronounce even quite right. The setup of this architecture has evolved a lot over time. In the end, we want the nodes to all report back to a main server that aggregates the measurements and creates the map for you. And we use this MQTT or mosquito type of structure to do the message passing between the sensors. The nodes are down here, and I don't know why my pen turns itself off, but the nodes down here talk to this mosquito broker, and depending on the nature of the task and the intended subscribers, I guess, is how it works with tasks. So people publish data that they have. So it's a subscriber publish model where subscribers listen for specific keywords or buzzwords, and then when they show up in this broker, they pull the message in and process the data, and then post the results of that processing back to this broker, who then presumably another group or computer will pick that up because it's listening for the results of the processing. There's a Mongo database structure, which is a relatively unstructured database utility. There's something called Flask, which I don't know what it is. There's most of our programming is done in Python, which students love. It's used everywhere now, and it's got so much support from endless numbers of users groups that it's natural for a lot of these things. Whether it's, C is a little bit lower level, obviously an important part of things, but Python runs a lot of the control and a lot of the processing.
We have one more question.
Yeah.
What defines occupancy in your ground truth? Are the emitters sending a signal across the whole bandwidth that you are observing?
Right. So occupancy here is entirely based on whether or not the power in a given bandwidth exceeds a threshold. And we could prescribe that threshold. So it's a user controlled. So it's a strictly a 1-bit result. Take the power in that bandwidth, look at it, see if it's over, say, minus 80 dBm, whatever the number is, the magic number you want, and then report yes if it's true and no if it's not. So yellow is indicating it is over a threshold, and blue in these pictures was not. So I guess one of the things I want to emphasize on this one is that we've actually adopted our platform for various other types of sensors. So the whole intention of this platform was to allow heterogeneous types of sensor network, not just, say, the RadioHound. So it's not specific to particular sensors that we're using. They can use SDRs, and we have used other SDRs, I think, made by National Instruments. We've used also, we also in this lab have a heterogeneous group of sensors. With other faculty here at Notre Dame, we've used optical and infrared sensors as well, and used the same basic reporting structure of MQTT. I don't think I need to talk about these tasks here. We're running a little low on time. So we have a web-based GUI, and you'll see more of that with the demo, which I'm going to allow at least 15 minutes for here. We have various periodograms, waterfalls, heat maps. We can zoom in and out of things. We can look at the nodes, control the nodes in a variety of ways, set them up to frequencies, powers, bandwidths. We can do database queries on historical scans done with a particular node. That becomes a little bit more interesting when we look at some of the capture data we did with a trial run with the Federal Communications Commission and the United States Postal Service. So as I've mentioned, some of the things we're trying to do is to streamline the sensor. We want to get knock pieces out of the sensor, make it lower cost, drive down its power requirements. And question is then, the more we knock back on this sensor, how many more sensors do we need to compensate for the fact that each one of them is being made less capable, so to speak. So that's one of the future directions where we're headed. The other future direction, and related to our proposal to the NSF for the Spectra Initiative, is increase its tuning range, bandwidth, and applicability up to as much as 60 gigahertz. Right now, we have only a 48 megahertz sampling rate on our A to D. We want to get much higher bandwidths if we can, but again, at some cost of power, of course. And if we go to 60 gigahertz, power is going to be dramatically increased as well. I think that's one of those things that we would really appreciate the 1-bit sensors for at that point. We've had some engagements. We view those engagements as co-development, meaning it's not like a customer and or a client type relationship, but rather we don't necessarily know what features people want. So if we engage with people, we actually learn a lot in the process of what people want, and it helps to harden our whole system. To that end, let me say just quickly, we had a recently finished trial. I think it ended in May, where several of our sensors were used in some regions around, where is it, Boulder, I think, or is it, I forgot now exactly where it was.
Longmont, Colorado.
Okay. Where they did scans. The FCC has been requested by Congress at some point to do a feasibility study on what kind of coverage the U.S. has in terms of broadband. And the only way I think that we could get anything reliable on that is to actually make measurements. So throughput measurements with phones and or power measurements with devices. So you're seeing our device here as part of that feasibility study, along with some phones taped to a box. And this box is mounted on various USPS vehicles. There were, I think, 7 of them running at any given time in a relatively small scale study, but with a lot of data to be collected. And with the hope that if this ends up proving as a successful way to map out spectrum usage throughout the US, that this will scale up to the 200,000 vehicles that are USPS vehicles that are out there. You'll see some of that data in this demo. Randy?
All right. Can you stop sharing so I can share now?
Yep.
Thanks. So as Bert mentioned, there's a lot of pieces that go into this. Yes, the individual hardware is super critical and super important, but part of the allure of this system is being able to take the many disparate nodes and bringing them together into a single unified dashboard. As we see here, there's a number of nodes online. Most of them are just running one of our production branches. We see a couple of nodes that were being tested for various things and have dropped off the network a little bit. One of the things that's useful is just being able to go into a specific node. We see where it is in the map. We see some of the details being reported from the node. And we can just kind of bounce through here. I can come in, I can choose a frequency, choose a bandwidth, gain, number of samples, etc., and be able to do a real-time scan on that node and see what it's seeing. We see a little bit of a signal here at 900 megahertz, and it's reporting about negative 74 dBm. As mentioned, we do have particular bandwidths that we can do in these. The Beagle here has a 20 megahertz bandwidth, hence this range, but we're also able to do a much larger bandwidth scan, and it'll take multiple individual scans, stitch the results together, and pass that back to us. So from here, I can kind of zoom in and play on the map to figure out if there's something of interest at any of these particular frequencies. We also have the ability to come in and do a waterfall scan. So we're just going to do recurring scans and plot everything visually here. Let's reset the scale so it's useful. And we do see that there is that traffic at 900 megahertz, and a boss is paying attention in the other room, and if he starts moving it around, you can see on the waterfall plot, yes, it was there, now it's moving, and we can kind of track it visually over time to get a feel for what's happening with it. We tend to use this frequently in the lab as we're testing things, just to kind of see, you know, as I provide some other interference or some other alternate input to the board, what's happening with it and how long did it take.
Sorry to show you Abbas here. He's got a little transmitter or signal generator on a cart that he's pushing around and changing the frequency of. So it's not totally staged, this whole thing.
So one thing that wasn't really mentioned, but the system was originally designed with kind of a dual purpose mindset. One is the real-time scans of nodes like we've just done here. I want to go query a node. I want to see what it reports right now. The other is, as was used with the FCC and the post office experiment, being able to track and put these in as basically background scanners. Just set them up with specific scans they're going to run, let them run that repeatedly, and be able to visualize that data after the fact. So we can come in here, specify some date ranges. I've got a few quick pick things to make it easy, especially for the FCC test, because I'm never going to remember those dates. And we see right now the nodes currently at Notre Dame, but if I pick one of these scans here, we'll pop the map over. We zoom out a little bit. We see we are in Longmont, Colorado, where the experiment took place. And each of these dots just represents a single GPS or a single periodogram scan at some interval at some GPS location. So we can plot everything on the map, and you can kind of poke through and see where are some interesting scans, what do we have if need be.
And point out that these are very high bandwidth. These are from 600 to 2400 megahertz. So 1800 megahertz of bandwidth, I believe at a 15 kilohertz resolution or something of that nature.
We do have a question. What is causing the rise on the noise floor from the bottom of the 20 megahertz range to the top of the range?
Yeah, we do have some observant people on this call, I guess. The sensor is not perfect. It has some sort of a slope in one of the filters there that our next version we think is going to get rid of.
So as mentioned, we have about 1800 megahertz in frequency here. There was some target on the low end, so we could zoom in and kind of pick a particular frequency and just kind of see what it observed at this location at this time. If we want, we can bounce out and go to the high end as well. And for those who have the spectrum maps memorized, you'd be able to know that, oh, this frequency corresponds to this carrier at this band, et cetera. That's not my forte, so I won't pretend to know them. As we've done here so far, this is all on an individual node. To note, one of the other interesting aspects here is I'm not locking this node in any way. So if Boss or Bert or somebody else in the lab wants to do scans on this node at the same time, we both send in our tasks, our commands to the node, and the node processes them in FIFO order. So it will respond to both of us as if we were the only user on it. One of the other interesting aspects of using this dashboard is the ability to take multiple node periodograms and graph them all on top of each other. So we have the same UI as before, same range and frequency targets, but with the multi-node, I have the ability to come in and I can pick, let's just do these nodes in the room. Actually, no, let's do.
Yeah, this happens to be just a selection of nodes throughout a room here that's approximately, what, 30 by 20 feet or 30 by 30, 40 by 30, something like that.
So now I'm just doing a recurring scan every half second, just querying the nodes and seeing what they see. And as you can tell, the lower half here, these are the 2 megahertz version 2 nodes. And the upper band here is the version 3 nodes reporting at the 20 megahertz range. And as you see the spikes moving around, that's a boss tweaking the frequency and moving it around. And you see the system is fairly responsive to changes in the signals coming in.
I know somebody's going to ask, they're going to say, what are some of these other spikes and why is the 2 megahertz have a lower noise floor? There are a variety of issues relating to how many number of samples we're doing and the fact that probably some of the 2 megahertz nodes are overloaded a little bit to get these extra spikes.
So we do have a waterfall feature here as well. I don't know that I really recommend doing this for multiple nodes purely for the fact that it's going to plot every scan from every node as an individual line in the waterfall here. So this may not be the best troubleshooting tool for doing some research, but it is visually interesting to say the least. I wanted to tweak the scale I can. If it responds. All right, well, we'll pretend that worked. Probably one of the more interesting and fascinating pieces that we have in the lab to do the real-time scans is being able to pick the nodes and do 900. We'll start a heat map here. So now we're just continually sending requests to each node at that frequency in the range, getting the results back, doing an emitter estimation check, and seeing roughly where we are. Now, Abbas is standing about here in the lab right now. And as he starts to proceed around the room, we start to see that source estimator moving.
The right side of the picture is roughly equivalent to the right wall that Abbas is moving along.
Now he's about here.
And as you can tell, of course, things are pretty complex at 900 megahertz in a room full of scatterers and obstacles. Now he's coming around near me where I have a sensor right here. I have an antenna.
Thank you, Steelcase.
So this, emphasizes the fact that we can incorporate the measurements of lots of sensors now in something meaningful. Now the first half of the talk where I talked about the occupancy maps and the neural networks and all, that's not yet integrated into this map that you're seeing here. So we can't see quite the same pretty pictures and occupancy drawings that you saw, but that's at least part of what we're trying to do. We're trying to make sure that this system can actually create those nice occupancy maps based on the readings of, say, 100 sensors over a relatively large geographic area. So we could say we're 50% of the way there. Thanks, Abbas.
I will point out this orange node, which I do not have selected in the test here. It is tied to an active GPS antenna that's sitting on top of the building. And that's why you see it kind of bounce around as the GPS sensitivity just kind of reports different ranges every time, but it's still within the, whatever the accuracy it is. The rest of the nodes we do have hard coded in the lab, mostly because they're indoors and there's no GPS. So we just kind of laid it out and presented it this way. So it's a nice, easy to digest demo.
Well, Randy, we're at 2 minutes left. Anything quickly before Tiffany calls us on it?
No, nothing from my side.
Maybe we could throw it up.
We've got a question. What 1-bit diode sensor is used?
Oh, that's an interesting question, Alan. In the presentation I gave, that was a theoretical type of description of what would happen if we used a 1-bit sensor. But part of our project that I didn't describe here, it's with an operator, service provider, is to use 1-bit diode sensors at 39 gigahertz. So we're trying to use some of our 1-bit knowledge of what happens with 1-bit sensors up in millimeter band. We think as we get higher and higher in frequency, the loss of resolution will be more and more beneficial in the sense of saving us power. And so we're not doing too much of 1-bit stuff hardware-wise down in the lower bands. Does that make sense?
We have another question. One negative aspect in using cheap sensors is the radio characteristics, filters, calibration, etc. are less than ideal. You may find that a radio is reporting occupancy where there is none. Does your spectrum sensing mechanism have a way to compensate for the cheaper hardware?
Well, so far we've been pretty pleasantly surprised with the way the machine learning methods seem to, so when you train a machine learning algorithm, you feed it using the sensors you think you'll be using in the field. So if they're if they have imperfections, calibration, poor resolution, interference, then as long as you use those sensors during training and give it accurate occupancy to learn from, it does a relatively good job of using those same sensors to estimate occupancy. At least that's what we found. Of course, that's not again, we're relying on the magic of the neural net to help compensate for the fact that if you're using poor sensors, that as long as you use enough of them, the neural net seems to be able to compensate for the fact that individually they're not so good. Anything else?
Yeah, I have a quick question. Instead of typing it, because I'll probably take forever. Is the genesis behind this effort kind of from the FCC standpoint or the commercial world to essentially distribute these across like a metropolitan area and monitor the RF spectrum for interferers now that it's going to get so congested with all the different IoT protocols that are being distributed out there or deployed, along with like all the cellular to include 5G. So is that kind of what the genesis behind this effort was?
So I think it's fair to say that our original genesis was, and this was, of course, 5 years ago or more, around 5 years ago, was that it'd be kind of neat if we were able to do a sensor, because there's a lot of push right now from the commercial, at least from the non-incumbents on the commercial side, to share spectrum. And also from the defense side to have spectrum awareness and what they call RF situational awareness. So we thought that if we could create this kind of sensor network and try to drive the whole effort into a very low cost, low power regime, that it would possibly serve, we wouldn't know how the world would evolve, of course, in the commercial world, but we thought it might serve a lot of possible purposes down the road. Now, we didn't foresee, for example, this congressional mandate where they're trying to get to whatever's the ground truth. And of course, any kind of a knowledge of policy or any kind of activities going forward, given how congested spectrum is, and the lack of knowledge of what actually is being used where and when, it's conceivable that you would want an accurate spectrum map at any given time of say the US, to the extent that you could, so that you could make accurate decisions on, because it's hard to believe when anyone says about any licenses they're using unless you go out and actually make the measurements. So to the extent that this sensor could help to serve that purpose, that's the kind of ideas that we were thinking about. Does that make sense?
Yes, absolutely. I appreciate it, because I've also seen, I think University of Washington was doing something called CGlass. It was more for like cellular interferers and stuff like that. So I was just wondering what the genesis was. I appreciate your answer. Thank you.
You're welcome. So Scott asks about how other people might be involved, and Randy, I think, responded. Indeed, email addresses of myself. You can always go through Nick Lanneman as well. He's of course intimately tied into the things we're doing here. So Randy, myself, or Nick, or any one of us will steer in the right direction if you want to, if you have further interest in any of the details.
That might be a good place to say thank you to Bert. If you have some time to stick around and address additional questions, that's fine. But we advertised the session from 1 to 2, and so maybe we should cut people loose if they need to go. Let's quickly thank you, Bert.
Thank you. Thanks, Randy. Thanks, Abbas.
And Randy and Abbas, of course.
Thank you.
Are there more questions and discussion?
I guess just one last question. Are most of the point of contacts actually on the web page, the Notre Dame wireless, the RadioHound portal site? Because I'm not going to be able to remember everybody's contact info or who I should direct questions to. So would the website be a good avenue for that? Over.
I can actually.
Yeah, go ahead, Tiffany.
I was going to say I can send you everyone's contact information if you would like.
And if you do the RadioHound search on in Notre Dame, then you'll be there's a web page that has further information as well.
Perfect. Thank you both.
Oh, hello, Ken. I didn't see you there earlier.
Hello to you, and thanks very much for your presentation. I'm going to have to check out now anyway.
Take care, sir.
Bye-bye.
Heath, you had some good questions there. Can we ask you where you're joining us from?
Oh, yeah. I'm sorry. I didn't introduce myself at the beginning. Yes, I work for the Navy.
Great. Any other comments or questions, suggestions before we close down? Going once.
Nice talk, Bert.
Thank you.
I think it's fair to say that we've come to realize that this is a really big problem, and we're very open to collaborating and building a bigger system and a better system.
Oh, by the way, for other people's reference, Ken Baker, who was there, I said hello to, was one of the FCC contacts we used, who helped us do the experiments out in the Denver area.
Okay, well, thanks again, Bert, Randy, Tiffany, for getting us organized, and everyone for joining. I think we're going to close down for today, and we look forward to some follow-up.
Bye-bye.
Bye now.